嗯，是。猫，对不对？笑死，猫们，喂得下。嗯哼。看到猫。Okay, we'll start at 7. Start at 7. Yeah, so this week, um, I'm planning to finish up the Dedekind's cut, which is actually a bit more ambitious. I'm not sure. It will be quite amazing if I can finish Dedekind's cut, all the details of Dedekind's cut during this stream. Okay, and yeah, that's the idea. But I'm pretty glad that um, last of my two videos did pretty well. The Coriolis Force video and the classical versus modern analysis video, which is what we're doing in this stream. So, and as for the stream, I made a summary video for the last stream because the last stream is where we started doing actual math. For the most part, we did a little bit at the end of the first stream, proving the square root of 2 is irrational, an old favorite. And anyway, because these stream recordings are pretty long, right? And so I just wanted to make a compressed version of what we did, and not necessarily going into all the details, but just the summary of the activities that we did. So that will help people to rewind, or even help myself, because lots of the details are quite intricate. So actually, before we start, I'm interested where my viewers are from. I'll go first. I'm in Canada right now, but I was not born here. So if you want to comment where you're from, you're more than welcome. Let's say hi to each other. Okay, it's now 7 o'clock, so on my end, 7 o'clock in Eastern Standard Time. It's when we start the stream usually. So let's begin. So last time we finished reading. Actually, let me put it on the main screen here. So last time we finished reading the coverage of Dedekind's cut in Whittaker and Watson, and discovered that it is only a sketch that is provided in the text. Okay, so it provided the motivation for Dedekind's cut. What does it mean to define a real number as a Dedekind's cut? Right? And then we considered the usual arithmetic operations and order relations between members of the Dedekind's cuts. Let's say, how do you compare two real numbers if we are treating a real number as a Dedekind cut? And also, how do you define additions? Additions, multiplications, subtraction, multiplication, division, all sorts of stuff between Dedekind cuts. And we want these operations to behave in the usual way. Right? So let's say, for example, we want the addition to be commutative. A plus B equals to B plus A. Right? We want these things to hold. So therefore, there's a lot of details that is left to be checked in this section. In the textbook, only one proof is given. Okay, in the section on Dedekind's cut, only one proof is given. And that's the proof that addition is closed. Addition is closed. Not even the usual algebraic laws. Okay, just the fact that that addition is closed, meaning if you add two cuts together, you get another cut. And here's the proof given by Whittaker and Watson. And that's about it. Okay, so which means we as readers have to fill this up. Okay, and I know it's tempted to jump into the later section, and this is actually the tendency of most analysis courses, just to state the axioms of the real numbers, and then see, okay, what do these axioms by us, which is fine, which is not a problem in itself. But the whole point of Dedekind's cut is to show that these axioms aren't self-contradictory, because at the end of the day, you can give any axioms you want. If the axioms are self-contradictory, then everything is vacuously true. Vacuously true is a concept in logic that says if the premise of a sequence of deduction is false, then regardless of what conclusion you put forth, the whole argument is always true, just by the virtue of vacuous truth, which is not what we want, obviously. Right? So we wanted to have we want to be confident that the usual properties of the real numbers that we assumed since high school are not fictions. Okay, so that's the whole point, and that's why the completeness of the real actually, or maybe you should talk more about that later, but just the axioms of the reals sits at the very foundation of analysis. So for that reason alone, I think it is well worth the time to go through the details, and once only, because after we've done that, we'll never come back, hopefully, okay, hopefully we'll never come back to Dedekind's cut again, and instead just work with the usual axioms of the real. Okay, so that's about the importance of this stuff. But what we started doing last stream is here, and by the way, this is a a glimpse into my one of my future videos, by the way. It's got to do with linear regression. Okay, but anyway, advantage of those who came to the stream. Anyway, I'll close this. We'll focus on the Dedekind's cut. So what we started doing last, at the end of the, and actually for the good second half of the last stream, is to recasting everything in terms of modern notations and including set theory. Okay, because the language in Whittaker and Watson are somewhat dated for obvious reasons, because this was written at the beginning of the 20th century. Actually, it was near the end of the 19th century. So it was at the time when the language, the common foundation of mathematics, at least for the mainstream mathematics, is far from clear. So we want to, so to say, to set things in a form that is suitable for, or at least more well versed by modern readers. So, because in the original definition, a cut consists of two classes, the L class and the R class. For example, the Dedekind's cut for square root of 2 has a R class, which consists of which consists of positive rational numbers whose square exceeds 2. And the L class consists of all the other rationals. Right? So in the original definition, there are two classes. But we know that the L class is just a complement of the R class, and vice versa. So it will be easier that we just define one class, and you don't lose the other half, right? So you don't lose any information. The other half is simply the complement of the one of the classes we picked. And so for that, we redefined. Okay, we redefined the Dedekind's cut as follows. Definition: a cut is a subset alpha of Q with the following properties. Okay, the alpha is not empty, nor is it equal to the whole of rationals. So that's the first property. The second property is that if P is an alpha and Q is another rational that is less than P, Q is immediately an alpha. So everything to the left of P. Okay, so if P is an alpha, then every rational to the left of P is automatically included in alpha. Okay. So this is to capture the idea of an interval, even though we don't speak of rational intervals. Okay, we don't speak of intervals of rational. Okay, interval is something we only discuss once we constructed the reals. Okay, so this behaves like an interval, but not quite. Okay, so that's the second property. And the third property is that any cut has no greatest element. So if P is an alpha, then it's got to be another element in alpha that is greater than P. There's always something. There's always something to the right of P. And actually, Dedekind himself gave a marvelous proof that the square root of 2 in a cut for the square root of 2, the left class has no greatest element and the right class has no least element, using a single expression, which we verified last time. Okay, so I won't get into the details because it's kind of tedious, but coming up with this construction to show that at least a greatest element does not exist in the left class is quite ingenious. All right, so now we're just taking these factors, not these factors, these properties as our definition of the cut. Okay, and then we define the relationship less than between cuts. Okay, the relationship of less than between cuts. So it's just a proper containment relationship. So by alpha less than beta, we mean that alpha is a proper subset of beta. So we're going to use the same notation for both the less than, for both the order between cuts and the order between rationals. the same notation. Both are used in less than. Although technically speaking, we should distinguish those two because the meanings are different, right? Because here we're talking about the usual relationship between irrationals, which is taken as given, right? So when we're doing Dedekind cut, we already assume the existence of Q, right? The existence of the rationals and all the other usual operations and orders are defined on them. So this is when we write R is less than S, this is the usual order relationship on Q that we're talking about. But when we write alpha is less than beta, we mean this very specific order relationship that we just defined. So it would be better if we write R less than with a subscript Q, S, and alpha less than with a subscript of R, because later we denoted the set of all cuts to be big R, and then beta. It would be better if we write it that way. However, it's a pain in the butt to write that, right? It's not fun. So instead, we distinguish these two relations by choosing different classes of letters. So for example, we only use Greek letters for cuts. Okay, we only use Greek letters for cuts, and we also only uses the Latin letters for the rational. So this way, which relation we're talking about is clear from the context. Okay, and so in order to be a order, a order. This is actually a total order, but since we're dealing with reals here, okay, so we're dealing with reals here. We're always talking about total orders. So the order, in order to be a order relation, we defined what a general order relation needs to satisfy, namely these two properties. Okay, so these are the order axioms. Right? We just defined a concrete order between cuts, so we need to verify that it is actually a bona fide order. Right? We need to verify the trichotomy property, right, for every x and y. Exactly one of the three is true, and also we need to show that it satisfies the transitivity property. Okay, so this is exactly what we did. Right after defining the order, okay, the transitivity and trichotomy, and after that, we have a big theorem. That is, we show that the collection R of all cuts equipped with that order relation satisfy the least upper bound property. So the least upper bound property is absolutely crucial. This is the distinguishing feature of the reals versus the rationals. So the rational does not have the least upper bound property, but the real does. That is, if we have a subset in R that is non-empty and bounded above, okay, then it must have a supremum, or aka least upper bound, and that least upper bound is also in R. So what this says is, if we take a non-empty collection of cuts that is bounded above, namely has an upper bound, and by the way, the upper bound is understood according to the order relationship between cuts. We have to be extremely consistent. Now, if that's true, there is another cut. There is another cut that is in R that serves the least upper bound of A. So in the proof, we have to construct such a soup. And this is exactly what we did. We take the union of all cuts in A, and we show that this candidate cut is indeed a cut, first of all. If it's a cut, then it's in R, right? Because R is the collection of all cuts. And second, to prove this is an upper bound. To prove this is the least upper bound. Okay, so and now we are in a good position to start defining arithmetic operations. So let's start here and define the set that represents the sum of two cuts. So definition. Okay, definition, and let's see if alpha and say beta are in R. These two are cuts. Okay, we define their sum, their sum, aka addition, alpha plus beta, to be the set of all R plus S, where R is in A, where R is in alpha, and S is in beta. So just define the addition in the usual way. Right? So that is to say, in set notation, we have alpha plus beta equals to R plus S, such that R is in alpha and S is in beta. Okay, and that's it. So that's the definition of addition. So immediately several questions arises. So this is a cut. We need to show that this is a cut. And then the addition properties. Okay, so let's first show this is a cut, and then we list all the properties that we wish it to hold. Okay, and then prove it accordingly. Okay, so proposition. Addition, as defined above, is closed in R. It's closed in R, i.e., if alpha and beta is in R, alpha plus beta is in R. Okay, so let's prove it. Okay, so as usual, let's start by assuming the assumptions. Assume, or just let alpha, beta be in R. We need to show that alpha plus beta is a cut. This is essentially we redoing the proof in Whittaker and Watson, but using our axioms. All right. So what's a cut? This is actually a very common practice we'll be doing a lot, is always going back and copy the definition, okay, and then verify them one by one, okay, going back and forth. So this is all the requirements of a cut, okay. So 1. Let's prove 1. Alpha plus beta is not empty, nor is it the whole of Q. Okay. So we need to do that. Okay. I'll remove this part when I'm done with this proof. Okay. So this is what we need to do. Actually, you just write it this way. Not empty and not the whole Q. But this is clear because if you have two cuts, then these two are not empty. Since alpha and beta are cuts, sorry, they are not empty. They're not empty, and thus so is alpha plus beta, right? Because you take an arbitrary element from alpha and an arbitrary element from beta, add the two rationals together, you get an element in alpha plus beta. So alpha plus beta is non-empty. Easy. So why it is not the whole of rationals? To see alpha plus beta is not the whole of rational, not equal to the entirety of Q, we take something that is not in alpha, right? Because alpha is not the whole. We take let's say R prime in alpha and S prime in beta. Sorry, not I meant not in. Okay, not in. No. Some rational R prime not in alpha, and some rational S prime not in beta. So that's what we're picking. Okay. They exist since they exist since alpha and beta, alpha or beta, are not the whole of Q. Okay, and so clearly, for all R in alpha and for all S in beta, R prime is greater than R and S prime is greater than S. Actually, here we're using a little proposition that we prove after giving the definition of cut. So the two propositions are such: if alpha is not in if R is not in alpha, and R is less than S, then S is not in alpha. That's one proposition, and actually that's the second proposition. The first proposition says if P is in alpha and Q is not in alpha, then P is less than Q. Okay, so we were using this one. Actually, you know what? I'll take these two down because they're quite helpful as we as our experience shown in the last stream. So these two are immediate. Sorry, this is not what I mean. These two were immediate from the definition of the cut, but they turned out to be quite useful. So here we're assuming R prime is not in alpha and S prime is not in beta, and so we have the ideal setup for proposition 1. R prime is greater than all the R's in alpha, and S prime is greater than all the S in beta, and thus so we can use the properties of inequalities between rationals. R prime plus S prime is greater than R plus S. Right. So, i.e., R prime plus S prime is greater than all elements in the set alpha plus beta. In alpha plus beta. So therefore, R prime plus S prime is not in alpha plus beta. So therefore, it's not the whole of Q. And as a result, alpha plus beta is not the whole of Q. All right, nice. Okay, so the first one is done. Okay, so I'm going to remove that. Okay, second, what do we need to do? Second, we need to prove that if if let's say P is in alpha plus beta, if P is in alpha plus beta, and Q is not in alpha plus beta, then we must have P is less than Q. Okay, we need to prove this property. So how do we do that? Okay, so assume P is less than, P is in, assume, P is in alpha plus beta, assuming the if part. So these are just like the mechanical steps for any sort of proof writing. You assume the if part, and Q is not in. Okay. Is not in alpha plus beta. Okay, we need to show that P is less than Q. So how do we do that? Okay. All right. So, well, P, then P is equal to R plus S for some R. Oops, that's not good. For some R in alpha, because that's the definition of addition, and some S in beta. Okay. This comes from assuming P is in alpha plus beta. Okay, so now we need to make use of the second assumption. Q is not in alpha plus beta. Need to show that Q is less than. Actually, I made a mistake. I need to show Q is in. I didn't copy this right. If P is in alpha plus beta and Q is not, I copied this proposition. I should have copied this. Silly me. So let's rewrite. If P is in alpha plus beta and Q is in big Q with Q less than P, that should be the correct. My God. Okay, sorry about that. So you see, that's why it's handy to have the definitions right next to whatever proof we're writing. I mean, even that I made a mistake. Okay, so here, rewrite the assumptions. So we're assuming Q is not, Q is less than P. So assuming that Q is less than P. So that's what we have, and we need to show Q is in alpha plus beta. So need to show Q is in alpha plus beta. Okay, that's our goal here. So, so by the assumption, P equals to R plus S for some R in alpha and some S in beta. Okay, so since Q is less than P, since Q is less than P equals to R plus S, we have Q minus S. Let's manipulate the inequality. We have Q minus S. Q is less than R plus S. So Q minus S is less than R. So Q minus S is less than R. So that means Q is in the same class or the same cut where R is in. So yeah, by one of the properties, R is in alpha. R is in alpha, and Q minus S is less than R. So Q minus S is in alpha as well. And this is actually the second property of the cut. I deleted the first one, so it reads 1. Okay, it's actually by the second property, by property 2 of cut. Q minus S is in alpha. Okay, that's what we have. Q minus S is in alpha, and Q minus S is in alpha, and what do we need? We need Q is in alpha plus beta. But Q, so thus, Q, we can write it as Q minus S plus S. So Q minus S is in alpha already, and S is in beta. Okay. Put it this way, Q minus S plus S. Q minus S comes from alpha, S comes from beta, Q is in alpha plus beta. Okay, and so therefore the second property, this property is shown as needed. Okay, great. Next up, so we need this property, namely alpha plus beta has no greatest element. If P is in alpha plus beta, then there exists R in alpha plus beta with P less than R. So we need that. Okay, and after that we're done with proving alpha plus beta is a cut. Okay, so assuming the if part, assume P is in alpha plus beta. So this is an existence statement. We need to exhibit an R in alpha plus beta with P less than R. Okay, so how do we do that? Assume P is okay. So well, let's just follow our previous proof of the proof of the previous property, right? Assuming that P is in alpha, right? So then immediately we can write P equals to R plus S for some R in alpha and some S in beta. This is what we can get. Okay, so we want to show that this new cut, this new cut has no greatest element. So why don't we use that very property of the cut for, let's say, alpha. Since alpha is a cut, we have something in alpha. R is in alpha. There is something that is greater than R in alpha. There exists T in alpha with T greater than R. Right. So that's, we're using the third property, property 3. Property 3 of cut. Okay. So this very property. Yeah. Okay. So let's work from there. So I want to use this T to construct an element that is greater than P, but is still in R plus beta. Well, T plus beta is greater than P, no? So then immediately we have T plus beta, not T plus beta, this makes no sense. T plus S is greater than R plus S, which is equal to P. T comes from alpha, S comes from beta. So T plus S is in alpha plus beta, and T plus S is greater than P. Okay, so that's right. Then T plus S is in alpha plus beta with T plus S greater than P. Okay, or P is less than T plus S, same thing. Okay, so that's what we wanted. Therefore, okay. Right, alpha plus beta has no greatest element. Okay, so therefore overall, hence alpha plus beta is a cut. Okay, and since alpha and beta are arbitrary, this proves that addition between cuts is closed. Addition is closed in R, right? So that's what we wanted. Okay, so at least this operation now makes sense. And now we need to give the list of properties that we wish the addition to hold. Okay, so these are so-called field properties. Field properties. So I'm clearly distinguishing two portions of the exposition. So everything written here, starting here, okay, before the three dots here, these are axiomatic definitions. Okay, axiomatic definition, like what is, for example, an order has to satisfy. But we never really gave a concrete procedure of how to decide whether two elements are in what order, right? So we just said, okay, whatever order relationship needs to behave in this way. Right? This is an axiomatic definition. It does not have any content. So we want to do the same for addition. Okay, we wanted to set forth of the desired properties of addition, and then we can work on, say, okay, let's define an actual addition between cuts and verify these properties. So let's define what we mean to be a field. Okay, by a field, we mean a set, let's say F, by a field. Okay, so we mean a set F that is equipped with two operations called addition and multiplication. We mean a set F equipped with two operations, plus and multiply. Okay. And multiplication. Okay. Which satisfy the following properties called field axioms. Properties known as the field axioms. Okay. So field axiom, we're going to group them into A, M, and D. Field axioms group A, M, and D. All right. So first we have A. A axioms of addition axioms or for addition or plus. Okay, axioms for plus. So how should addition behave? Okay, how should addition behave? So let's start with A1. A1 says addition is closed, which is what we just proved. Okay, so if x is in F and y is in F, then you can always add them and get a new element. X plus y is in F. Right? This is the closure property. So we proved that. Great. Second says addition is commutative, so that's x plus for all x and y in f, okay, x plus y is equal to y plus x. Addition is commutative. Commutativity, okay? So that's the second. So Whittaker and Watson only proved the first one. A3, addition is associative. So we need something like this. We need for all x, y, and z in f, x plus y plus z. You add the x and y together and then add the result is the same as x plus y plus z, where y and z were added together first. Okay, so that's the associativity. So we want the associativity to be true. Okay, A4. We need something called a zero. So what is a zero in a field? The zero is called additive identity. Okay, so that is F contains an element denoted as 0. Okay, denoted as 0, such that for all x in F, x plus 0 is just x. So this is A4 defines the additive identity, which aka 0. Additive identity must exist. All right, so that's the fourth addition axiom. A5 says basically you can take the numbers of opposite sign. Okay, additive inverse. So for every x in F, there exists an element denoted as minus x, such that it has the property that x plus minus x is equal to 0, where 0 is defined in A4. So this axiom is called the existence of additive inverse. Okay, so we'll do the multiplications axioms later. So these are the axioms for addition. Okay, so A stands for addition axioms, M stands for multiplication axioms, and D is a single axiom called distributivity. Okay, the usual distributivity in arithmetic. So basically, the group A handles addition alone, group M handles multiplication alone, and D handles how addition and multiplications interact. So we just defined addition between cuts. We have not yet defined multiplication. So the multiplication axioms are not of concerns to us yet. All right, so let's copy the, okay, I don't need this anymore. Okay, I need to verify every single one of them to know that the addition we just defined, okay, which we just proved that it is closed. Right. So this is so basically this is verifying A1. This verifies A1. Okay. Axiom A1. Okay. So let's see. What is our next proposition? So we need to prove A2. We need to verify A2. Addition as defined above is closed in R. Addition as defined above is addition in R as defined above, as defined, I won't write above, as defined between cuts obviously, is commutative. Okay, namely, if alpha and beta is in R, alpha plus beta is equal to beta plus alpha. We need to verify that. Okay, so this verifies, if this is done, this verifies A3. Okay, so let's start the proof by assuming alpha and beta is in R. Okay. Let alpha and beta to be in R. Okay, I need to show these two hold. Okay, and this is obvious, right? This is very obvious because then alpha plus beta, because it boils down to the fact that the rational addition, the additions between rationals is commutative. Right? So this is R plus S. And by the way, you know what? Let's do this formally because I don't want to hand wave. This is supposed to be. I said in the beginning, right? So I said in one of the videos and the beginning that we assume a certain degree of familiarity with writing proofs, but if not, I mean, I'm trying to fill that gap by doing this rather elementary proof. So let's do that. Then we need to show the set equality, right? So we need to show these two are the same set. To show the two sets are the same, you need to show double containment. You need to show alpha plus beta is a subset of alpha, sorry, not beta plus beta. My bad, typo. Alpha plus beta and beta plus alpha contains each other. That's the definition of set equality. Okay. So want to prove that alpha plus beta is a subset of beta plus alpha and vice versa, and the other way around. Okay, so basically just reverse the containment symbol. Okay, so so let's first prove the first relation. Suppose let's say suppose P is in alpha plus beta. Suppose P is in alpha plus beta. Okay, then P is equal to R plus S for some R is in alpha and some S is in beta. Okay, so then well we can write it as P is equal to S plus R. So this way P is equal to something that comes from beta plus something comes from alpha, and thus P is in alpha plus beta. Sorry, it is in beta plus alpha. Right? It's completely trivial proof, but this proves the first containment. Okay. Utterly trivial. Okay, this proves this, and the proof of the other containment is similar. So basically, this boils down to R plus S equals to S plus R, because we already assume the properties of the rationals. So this is similar. QED. Okay, so this verifies A3. Very easy. Okay, so now let's set up the next proposition. We need, this is A3. Hang on, this is A2, right? This is A2. Sorry, my bad. This is A2. This is A2. So we need to verify A3. A3 says you have associativity. Well, I think this should also be very easy because addition between rationals are associative. Is associative. Is associative. Namely, if alpha and beta and gamma are in R, we have alpha plus beta together, and then plus gamma is the same as alpha plus beta plus gamma quantity. Right. So, hang on, I'll be back because I need to feed my cat real quick, okay? Just 2 minutes. Let's hurry. Okay, so this verifies A3 proof. Okay. It should also be quite easy. So let's just let alpha, beta, and gamma be in real. I think it boils down to the fact that addition between rationals is associative. All right, so okay, need to show a double containment relation. Okay, just to I use this for containment and not for proper containment. Okay, if it's proper containment, I will write a not equal at the bottom. So it's kind of like this. Okay, this is proper containment. If I just write this curve here, okay, this means just containment. So this is actually redundant. I try to be consistent as consistent as possible. Okay, so this should be if I can spot redundancy, I'll change them. All right, so okay, superset symbol. Yeah. So okay, so let P to be in this set. So what does that mean? Then P is equal to R plus say OPQ RS Q R Q plus R. Okay, for some Q in alpha plus beta and R in gamma. Okay, so since Q is in alpha plus beta, Q is equal to S plus T for some S in alpha, and T in beta. Okay, so together overall, thus P is equal to Q plus R. Q is S plus T plus R. Okay, so that's the original grouping, like so. Okay, so and this is of course equal to, and just continue and write S plus T plus R. So this is immediate. S is from alpha, and T plus R is from beta plus gamma. is in alpha plus beta plus gamma. All right, so therefore, so P is in the set, and this proves the first containment relationship. And by the way, this kind of proof has a name. Okay, it's called element chasing. To prove a set is a subset of another, this is called element chasing. You start from an arbitrary element in the supposedly smaller set, and you prove that it's also in the bigger set. Okay, supposedly bigger set. And the other proof, the other direction, is proved similarly. Okay, done. A3 is done. A4, we need to prove the existence of the additive identity. Okay, so proposition. Now, R contains an element called 0, denoted as 0, such that for all alpha in R, alpha plus 0 is equal to alpha. What would that be? What would that be? Well, we should think of 0 just as the usual 0. Just as the usual 0, right? So, except here, 0 is a cut. The cut that represents 0. So we need to actually define this cut. Right? So, well, that's just the cut that contains all the negatives. That's it. That's it, right? So this verifies A4. Okay, we first define 0, and then we verify the identity. This verifies A4. Okay, it's not very difficult proof. So we take 0 to be the set of rationals Q in big Q, such that Q is negative. So this is a set of all the negative rationals. Right. So this is our Q. This is our 0 here. Okay, I need to show. Obviously, this is a cut. Right? Obviously, this is a cut. Actually, you know what? Let's prove it. We need to show. And just to avoid confusion here, because this is highly confusable, right? So I'm going to, for the moment, I'm going to give it a subscript called Q0R. And the 0 without a subscript is understood as the rational 0. Okay. For the moment, we take this as our 0, but eventually we will drop the subscript. After this is verified, we'll drop our subscript, and it should be clear from context what exactly, which is exactly 0 we're talking about. Okay. It's like when you first learn about vectors, you like to put a vector symbol on top of 0, but later on you see it will never cause any confusion, so you just give up and just write the vector in the lazy way without any arrows, bold symbols, and so it's clear from context. Okay, so now there is a danger of confusion, so that's why I take the pain to put a R in the subscript. Hopefully that's careful enough. Okay, we need to show that this is indeed a cut. Is a cut. Okay, and it contains an element in R, right? So it's a cut. We need to show that, and for all alpha in R, alpha plus our 0, which we just defined, is the same as alpha. Okay, let's go. So 0R is a cut. Okay, well, we need the cut properties again. Going back, the definition of a cut. All three properties. Okay. Okay, so that's that's what we're trying to do. So this is clearly not empty. Actually, okay, 0R is clearly not empty. Not equal. Okay, not equal to the empty set. Since -1 is in 0. Okay, so the rational number -1 is in the cut 0R. This is what we mean. And okay, start a new sentence. 0R is not the whole of Q. Since 1 is not 0R. Done. All right. So that's 1, 2. If 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 P is in 0R, then what happened? If P is in 0R, then it must mean that P is less than 0. By definition, P is less than 0. So if Q is less than, if Q is less than P, then Q is less than 0. And Q is less than 0, and thus Q is in 0R as well. So that's the second property verified. The third property, if P is in alpha, so if P is in 0R, if P is in 0R, then there exists an R in 0R with P less than that. Okay, so P is in less than 0. Okay, and just take half P. Half P is greater than P because P is negative. We take Q equals to half P, and we have, actually we take R, okay? We take R equals to half P, and take R equals to half P, then R is less than 0, and R P is less than R. So R is less than 0, and thus R is in 0R with P less than R. Okay, so that's it. Okay, so this is indeed a cut. Delete this. Okay, we need to show the identity. So now let alpha to be in real, be arbitrary. Let's prove the identity. Okay. So once again, this is an equality statement. We need to prove both directions. Equality between two sets. Let's first prove one direction and prove the other. Which one is easier, by the way? Which direction is easier? We usually prove the easier one first. So let's think about that. So if, let's say, let's prove the first one. Suppose P is in alpha plus 0. Okay. And P is equal to R plus S for some R in alpha, and for some S is in 0R, right? So that's what we get from this assumption. Then immediately we have S is less than 0. So if S is less than 0, then R plus S is less than R. And thus R plus S is less than R. If R plus S is less than R, we can use the cut property, which we just deleted, but hopefully we can remember that by now. R is in alpha and something is less than R, that saying must be in alpha. Therefore, thus R plus S is in alpha due to the second property of the cut, property 2 of cuts. Okay, so now we have shown that is to say, P equals to R, which is in alpha. This proves the first direction. This proves the first direction. Alpha plus 0R is a subset of R. So that's the first direction proved successfully. So now let's work the other way. Starting with P in alpha, let's start from P in alpha and see if we can show that P is in alpha plus 0. Okay. So now we have, alpha, P is in alpha. To do so, we can use the third property of cut. So if P is in alpha, then there must exist something in alpha that is greater than P, because alpha has no greatest element. Then there exists P prime, let's call it P prime, in alpha, or let's just say Q. Let's just say we're not running out of Latin letters to use prime notation yet, okay? So there exists a Q in alpha with P less than Q. This is property 3 of cuts, no greatest element. All right, so therefore, this Q minus P is positive. Actually, you know what? We want something negative because we want it to be in 0Rs. We need something negative. Q minus P is negative. And that's Q, and this Q is IE. U minus Q is in 0R. Okay? So now we can write it as, we can write P equals to Q plus P minus Q. So see what we're doing here. The first element comes from alpha, the second element comes from 0R. So this is in alpha plus 0R. That's the second direction done. This proves the other direction. All right, cool. So that's everything finished. Okay, for this proposition. Put a QED symbol here. A4 done. Okay, A5. For every, okay, let's set up the proposition. For every alpha in big R, there exists an element denoted as minus alpha, such that alpha plus minus alpha is 0. Okay, so let me put a remark here. From now on, we simply suppress a subscript double R in our 0 element. Whenever there is no confusion arise. When there is no confusion. Okay, so that's it. So basically, the meaning of 0 is, if the meaning of 0 is clear from context, we can just write 0. Which is exactly what we did here, because alpha plus minus alpha, this refers to the addition between two cuts. So you should get a cut. It's not a rational 0. Okay, so that's what we're doing here. So we need to show the existence of minus alpha. So once again, this is an existence proof, so we need to construct the minus alpha. Okay, all right, so, okay, how do you define this minus alpha? Proof. Let alpha be in real. Okay. Let's define the minus alpha to be, actually, you know what, let's just call it beta, and eventually we will verify alpha plus beta is equal to 0. Okay. So how do you put get the negative part? So let's do some scratch work. So, okay, we can get rid of these axioms now because we already designed our propositions. Okay, so how do we define the negative of a cut? All right, so this is alpha. Everything to the left, okay? And let's suppose 0 is here. Suppose alpha is greater than 0 for the moment. What should be minus alpha? So minus alpha should be this cut right here. Or which we denote just as beta. Okay, so we want to describe this set based on this set. So what should beta look like? Let's write beta is the set of Q. So let's consider an arbitrary Q in beta. So let's first define the beta and then prove it has the desired property. Let's say Q is here. So that means minus Q should be here. Minus Q should be here. So beta is the collection of Q such that you know what? Let me use P. Beta is a collection of P such that minus P is not in alpha, right? And that's a good start, but not enough. Because what if minus P sits right at the boundary? Right? Because due to the nature of the cut, P should not be an endpoint of beta. So we want to emphasize that as well. So minus P should be here, but it needs to be strictly greater than the boundary of alpha, if that makes sense. So we want minus P to be strictly greater. So we can write minus P minus alpha to not in minus P minus R to be not in alpha for some R that is positive. For some R that is positive. So this R stands for irrational, okay? This is not a relationship between cuts, but this is just a rational. So this is what we mean. Minus P is here, and minus P minus alpha is, minus P minus R is here. So you can always squeeze a point between the endpoint of alpha and minus P. This way, it ensures that minus P is not an endpoint of alpha. So that's our definition for the negative. Okay, so we define the negative to be this way and hope that it will satisfy our desired property. So let alpha be in R. Define the set beta to be define the set beta to be the collection of P such that minus P minus R is not in alpha for some or let's just say exist R positive. Exist R positive such that minus P minus R is not in alpha. Okay, so that's our set beta. We want to show that this satisfies alpha plus beta equals to 0. Okay, so, and also we need to show this is actually a cut. Okay, this is actually a cut. Need to show. So I need the cut properties again. Beta is in real. Okay. And the identity holds. Alpha plus beta is equal to 0. Okay, and I'm not going to bother writing 0R anymore. Okay, so that's the plan here. Okay, so this is what we need to do, and going back, we need the cut properties. 1, 2, 3. Verify that the minus alpha, aka beta, in our case, in our proposition or construction, these 3 properties of the cuts are satisfied. Okay, so starting with 1. Beta is a cut. Beta is a cut. Okay, going from 1. Beta is not empty, and beta is not the whole of rationals. How do we do that? Okay, how do we show that beta is not empty? Well, beta, we need to find something in beta, right? So let's take a look at the picture again. How do we construct an element in beta? So we need something that is not in alpha. So let's take something that is not in alpha, which of course exists. Alpha is not the whole real, not the whole rationals. Okay, so there is something that is not in alpha. And if we take, let's say S is not in alpha, and the opposite of S, is, how do we construct that? Okay, the first property of beta is a cut. Seems to be a little bit tricky. Need to show that beta is not empty. Beta is not an empty set. Okay, since alpha is not empty, well, it's a cut, so alpha is not empty. Actually, I need, alpha is not the whole of Q. So I can't find something that is not in alpha. There exists. S that is not in alpha. Okay, S is not in alpha. I want it based on S and construct something that is in beta. So let's see, just based on this picture, okay, S is here, somewhere here. S is somewhere here. How do I construct that? Let's say S is here, okay? And minus S should be here. And minus S minus 1 is in beta, right? I can't just take minus S itself because S might be at the boundary. And if I flip that, minus S is not in beta, see? So that's why I can't just take minus 1 on its own. So let's pick minus S minus S minus 1. Yeah. So let's take P equals to minus S minus 1. I want to show this is in the beta. How do I do that? Well, this is my P minus 1 minus minus 1, minus S minus 1. The opposite of that is S plus 1. So S plus 1 is greater than S. Okay, so then S plus 1 is greater than S. Then we can write minus P, which is S plus 1. Actually, can write minus P minus 1. Minus P minus 1 is equal to S, which is not in alpha, which is not in alpha. So minus p minus 1 is not in alpha. Minus p minus 1 is here. Actually, minus p minus 1 is just s. It's here. I need to show minus... Okay, what is the definition of beta? I forgot about that. Beta is... Yeah, so minus p minus r is in alpha. Yeah, that's it. That's what we wanted. Minus p minus 1 is in alpha. So by the definition of beta, hence p is in beta. Yeah, it's right in our face. P is in beta if there exists a positive r such that minus p minus r is in alpha. We have minus p minus 1 is in alpha by the definition of beta. Okay, so this proves the p is non-empty. This proves beta is non-empty as needed. Okay, next up, beta is not the whole Q. Beta is not the whole Q. So how do we do that? Oh, not the whole R, my bad. Beta based on this definition is not the whole Q. I want to construct a rational that is not in beta. That's enough. So let's think about something is in alpha. Let's think about something is in alpha. If something is in alpha, and based on the picture, let's say here, let's say Q is here. Let's use a different color. So imagine Q is here. So minus Q should be here. So minus Q should not be in beta. If I can show that, then beta is not the whole Q. So just take any Q in alpha. Take any Q in alpha. Let's see minus Q whether or not minus Q is in alpha. Is in beta. So minus Q. So does there exist an R positive such as minus Q minus R is in alpha? Is not in alpha? So something less than minus Q. So take any Q in alpha. Minus Q should not be in beta. Okay, let's. I can't make a quick. I can't make a quick proof. So let's suppose we're a contradiction, because it's right in our face. And is it the minus Q not in beta is right in our face, but I can't seem to prove it. Let's try a contradiction instead. Suppose for a contradiction that minus Q is in, hang on, suppose for contradiction that minus q is in beta. Let's say we claim minus q is not in beta, okay? Suppose for a contradiction that minus q is in beta, what do we get? So, well, just follow the definition. There exists R positive such that minus of minus q, then by definition of beta, here minus q is in beta, so the minus of minus q, namely positive q, is q minus r, is not in alpha. And that's a contradiction. Okay, so we see that for some alpha positive. Because this violates property 2 of the cut. Everything that is less than q should be an alpha, right? Q is an alpha, so everything to the left of q should be an alpha. So here we have found the contradiction. Contradicting property 2 of cuts. So that's it. Okay, so therefore minus q is not in beta as claimed. Okay, so there is something that is not in q. This proves beta is not the whole of q. As needed. Well, this actually was trickier than I imagined. Okay, anyway, I thought the main challenge is to prove the identity. But here, it turns out it took us a while to figure out that even the basic properties of cuts are satisfied. Okay, so yeah, unexpected things can happen when we try to prove things. Things turns out to be more difficult or easier. This can happen. So, all right, let's see what's our next move. We need to show minus p has satisfied the second property of the cut. Okay, so assume p is in beta. P is in beta, and q is in big Q. So I'm literally just copying the if part of property 2 with q less than p. Need to show q is in beta. All right, how do we do that? Well, let's use the definition of beta. Since p is in beta, there exists, or should we say, p is we have minus p minus r is not in beta, is not in alpha. Sorry, it's the definition. Minus p minus r is not in alpha for some r positive. Some positive rational, okay, R. All right. Okay, what to do here? We need to show that Q is also in beta. So Q is also in beta, so we need to show that minus Q minus something positive is not in alpha. All right. So can we go to the picture and see what that R should be? Okay. So let's draw a new picture. All right. Actually, let me just remove some of the elements here. Okay. So oops. All right. Want this to be, screw it, I'll just redraw a line. I want to be as bare bone as possible on the diagram. Okay, so this is my beta, and that was my alpha. I need to redraw the line. Okay. Basically, here I assumed P is in beta. Okay, so that's okay. This is my P, and so therefore minus P is here. Minus P is here. So you can write, you can put a point that is minus P minus R between minus P and the endpoint of alpha. So that's the idea. Okay, so I wanted to show that for this other rational Q is less than P. So the object of interest is Q. I need to show that Q is in beta as well. Q is less than P, that's given. So minus Q should be up here. So minus Q should be up here. If we use the same R, minus Q minus R should be greater than minus P minus R. Right? Q is less than P. So that means minus P, that means minus Q is greater than minus P. So you can put a minus R on both sides and the relationship still holds. So therefore, minus Q minus R cannot be an alpha, and we're done. Just take the same R. All right, so I think we can write it up now. Okay, so that's the that's our goal. Okay, since Q is less than P, we have minus Q is greater than minus P. Okay, and thus minus Q minus R is greater than minus P minus R. All right, so I think we have one of the properties come in handy. One of the basic properties for cuts that we proved right after the definition of cuts is right here. If R is not in alpha and R is less than S, then S is not in alpha. So that's this proposition we're using here. Okay, let me put that down. By property 2, underscore here. By this property 2, we have minus Q minus R is not in alpha. So Q satisfies the definition of beta. So by the definition of beta, i.e. Q is in beta as needed. All right, so second property of the cut is proven. Nice. Okay, third one. So let's assume P is in beta. Okay, so let's copy this down and modify it. Assume P is in beta. Then there exists, and we change that to need to show, need to exhibit something in alpha, something in beta need to exhibit some r in beta with p less than r. Namely, beta has no greatest element. So how do we do that? Okay, well, let's take a look at picture again. If something is in, let's say p is in beta, I need to find a q that is, or find an r that is greater than p and is still in beta. Well, this is not needed anymore. Just get rid of the junks. Okay, so this is our setup. We have p in beta. I want to show there is something in beta that is greater than p. Okay, so this is our minus p, and the minus p minus r. Minus p minus r. Minus p minus r is in beta, right? No. P plus r. I want to show that. So minus p minus r is here. Taking the opposite of that, you get p plus r. I want to show p plus r is in beta. And actually, you know what? Let's change the letter. Need to exhibit some t in beta with p less than t, so to say. And I let t to be p plus r. Let's see if that works. Okay, so assume p is in beta. Right, as we have p minus r not in alpha for some r positive. Okay. For some r positive. So is p plus r, take t, okay, take t to be p plus r. Okay, so thus p is less than t. So that's obvious. Right. We want to show that t is in beta. Is t in beta? Is t in beta? Well, if t is in beta, I need to show that the minus, there is something between. There's something between t and there's something between minus t and the boundary of alpha. So back to the diagram, this is my t, so to say, and that's not an ideal choice. Let's, you know what, let's pick t to be p plus half r instead. So this way, minus t is here. So immediately we have minus p minus r is less than minus t. Right. So that's I think that's better. So let's rewrite. So here the existence of alpha being positive is known. Okay. Since p is in beta, we have minus p minus r, not in alpha, for some alpha greater than 0. Okay, let's take p plus half r. Okay, then p is still less than t. Remains to show that t is in beta. So minus t. What about what's up with minus t? Well, minus t minus half r. Look at the diagram. minus t minus half r is exactly minus p minus r. So this is just minus p minus half r minus half r. So this is minus p minus r, which is not in alpha. Okay, not in alpha. So therefore, indeed, minus t, right? See, minus t minus something positive is not in alpha. So this proves, and since this, okay, minus t is in, minus t is, sorry, not minus t, but t is in beta. So now we have everything we needed. We needed t in beta and p is less than t. Okay, so as needed. Okay. Okay, so 3 is done. So this proves beta is a cut. Okay. Beta as a cut is done. What else do we need? Okay, we need to verify the final identity. Alpha plus beta is 0. So there's that. Let's go ahead and prove that. Once again, this is a double containment proof. Okay. So, well, let's prove the first direction. Let's say, and the opposite direction. Okay, so how do you prove the first direction? Let's prove the first direction first, okay? Okay, let's take, say, R from alpha. And S from beta. We need to show that R plus S is in 0. Is in 0, i.e. need to show R plus S is less than 0. Right? So here, this is where things can look confusing, but there's no possibility of confusion here, because R plus S being denoted as the sum of two Latin letters is a rational number, belongs to S. This must mean a cut, right? But the set 0, but the cut 0 refers to the set of all negative rationals. So it's just the same as showing R plus S is less than the rational 0. Okay. So even though this looks a bit weird, but there's no confusion here. Okay. So since S is in beta, what we have is minus S. We can't use R anymore. Let's just say minus S minus T is not in alpha. For some T positive, right? Actually, we just we have our diagram here. Right. Minus T minus S minus T is not in alpha. For some T positive, we must already have minus S is not in alpha. This is a weaker claim than minus S minus T not in alpha for some T positive, right? Because if minus s minus t is not in alpha for some t positive, then minus s cannot be in alpha. So this is not wrong. Okay. What I'm trying to get to is we have r is in alpha, and minus s is not in alpha. So immediately we have an order relationship between them. Right. R is in alpha, and minus s is not in alpha. Thus, r is less than minus s. Okay, then r plus s is less than 0 as needed. So we're done. Okay? This proves the first direction. All right. Let's prove the opposite inclusion. Okay, how do we do that? How do we prove 0 is contained in alpha plus beta? Okay, so let's pick an arbitrary negative rational. Okay, let's pick an arbitrary negative rational. We want to construct an element in alpha and an element in beta such that they sum up to whatever negative element that we start from. So let's put r to be in. Should we use a different letter? It doesn't matter. So let's just say r is in 0. Yeah, let's say r in 0. We need to exhibit alpha. We need to exhibit elements from alpha and beta such that need to exhibit elements, let's say P and Q, P in alpha and Q in beta, such that R is equal to P plus Q. So that's what we wanted. Okay, so R is in 0, then R is less than 0. Okay, R is less than 0. Nice. Did I spell this wrong? Exhibit. Okay, it's just, I think it's just word being weird. Okay, anyway. Okay, this is silly. What's going on? Okay, so how do we find such P and Q? Go back to the diagram again. So R is somewhere here. R is somewhere here. So let me just get rid of the junk here. Okay, this is my alpha and beta, 2 cuts. Okay. So I let R to be in 0. So this is my R here. How do I construct elements in alpha and beta? So I need a P and a Q so that they add to a negative number. So they add to a negative number. So that means if P plus Q is negative, that means P, by the way, is in alpha. P is in alpha. That means Q is less than minus P. Q is less than minus P. So let's say Q is somewhere here. P has got to be here. So this way, see, based on this scale, they add up to something negative. So that's what I want. Can we maybe pick an arbitrary P in alpha and then construct Q instead? Because constructing 2 things simultaneously is a little bit awkward. r is negative, then you can, based on that, construct a positive number. But the thing is, we don't know if alpha is actually shown as in the picture, no? So alpha, it appears here, okay? Here alpha is taken to be a positive real, but it doesn't have to be, right? So this is where things gets a little bit awkward here. I want to say some positive is in alpha, but this is not the general situation. The picture is not the general situation. Okay, but regardless, let's construct a positive number anyway. So, okay, since r is negative, or shall we say, let's take w to be minus half r. Then w is positive. And w is positive. Okay, we don't know if w is in alpha or not. We don't know that. Hmm. Yeah, I'm kind of struggling here. So how can we find a something that is in alpha? Well, can we at least find something that is not in alpha? Because beta has something to do with has something to do with something that's not in alpha. Hopefully we can work from there. Okay, so I'm going to use a property of the rational. So that means because alpha looks like this, alpha is not the whole of rational. You can find something that is not in alpha. You can find something that is not alpha. So basically here we have a positive number, w. Here we have a positive number, w. We can find an integer such that we can find a integer multiple of w that is not in alpha. So this is what we're going about. Okay, so well, by the Archimedean property, this is called the Archimedean property. So basically, you can think of Archimedean property as, let's say you have a little spoon, okay? The Archimedean property says if you scoop long enough, if you scoop water long enough, you can drain any ocean. You can drain any ocean in the world. Okay, so basically you can just scoop the water out once at a time. Okay, it might take you a large number of scoops, but you can do it. So this is called the Archimedean property. Okay, by the Archimedean how do you spell that? Archimedean property, yeah. By the Archimedean property of Q. Okay, there exists an integer there exists an integer n such that m plus 1 times w m plus 1 times w is greater than is not greater. We don't know exactly the upper bound of alpha, but we can say that it is not in alpha. Okay. Since alpha must be bounded above. Since alpha must be bounded above, otherwise it's the whole Q. Contradicting the property 1 of the cut. Okay, so we constructed something that is not in alpha. So something that is not in alpha. So let's say let's write, and then we take let's write the I want this thing that is not in alpha. I wanted to write it as a minus something minus a positive. Here W is my positive. Here W is my positive. So let's write it as m plus 1 W. Okay, m plus 1 W. Let's write it as minus. Okay, let's write it as m plus 2W minus W. So this minus W plays the role of minus R. Okay. And m plus 2W is my minus P. Okay? So this is my minus P. What we've done here is to, so basically we constructed the P. Right? So take P equals to minus m plus 2 W. Take P equals to minus P W, then we verify the property of P, and minus P minus W is equal to m plus 1 W, exactly as we designed, which is not in alpha. So this is not in alpha, and therefore P is in beta. Okay, so P is in beta, i.e. P is in beta. So we have something is in beta. Okay, so we have something P is in beta. So let me change the symbols here. So P is constructed. So P is constructed. I need to make sure that P and Q adds up to R, and that's easy. This is P, so P plus Q is R. Already have P, so Q is R minus P. Okay, R minus P. But I still need to verify this is indeed in A. Which is tricky because I didn't use any, we didn't have any property for A, right? We didn't have any property for A. How do I, we have R, okay, we have R, which is minus 2W. R, which is minus 2W. Minus 2W is what? P is, see, P has something to do with minus 2W. This is minus N w minus 2w and then plus nw, which is p plus nw. P is in beta. Is nw in alpha? Is nw in alpha? We don't know. M plus W is not in alpha. M plus W is not in alpha. We actually we have no idea. So, so let's rework this. We will rework this. Can I at least say alpha is positive? Can we at least say alpha is positive? I have R is in 0, therefore R is less than 0. R is less than 0. Okay. I think I need a lemma first. I need to first establish that based on this definition of beta, alpha and beta must have opposite sign. No? If I don't even have that, then I can't proceed. So okay, so let's first prove a after that proving this is a cut, let's before we prove this, let's first prove that alpha and beta have an opposite sign. Okay, let's have alpha and beta to be opposite sign. Okay, so then we claim something. Either alpha and beta are both 0 or have opposite sign. Or alpha or alpha and beta have opposite signs. Okay. We need that. So to see this, let's consider two cases. Actually, we need to consider three cases. We consider three cases. Okay, I'll finish this one. I'll finish this proof, the additive inverse thing, basically A5, the fifth addition axiom. This verifies A5. Okay, I'll finish A5 and then we call it today, but we need to do it properly. I don't want to hand wave over this. We consider three cases. Okay. So what are the three cases? So the first one says alpha is case 1. Case 1 alpha is 0. Need to show beta 0. So that's the first case. Let's set up our structure properly and then fill up the details. Case 2, alpha is positive. Need to show beta is negative. Okay. Case 3, alpha is negative. Need to show beta is positive. Okay. So let's do the first one. This should be easy. Alpha is 0, need to show beta is 0 as well. So if alpha is 0, then beta is equal to 0, we need to show a double containment. Let P be in beta, so to say. Let's first show that beta is contained in 0. Okay. Let P to be in beta. Let's see what happens next. If P is in beta, then minus P minus R is not in alpha. So for some alpha positive, for some R positive, for some R positive. So that's the that follows from the assumption P is in beta. Okay, I need to show P is in 0. I need to show P is in 0. So alpha here is 0. Alpha here is 0, so that means minus P minus R is greater or equal to 0. Since in this case alpha is 0. Minus P minus R is greater or equal to 0. Right, so that means P is less than or equal to minus, and thus P is less than or equal to minus R. And R is strictly greater than 0, so that means P is less than 0. So P is less than 0, therefore P is in 0. P is in the cut 0. Okay. Okay, so this proves that beta is contained in 0. This proves beta is in 0. Okay, so that's the first containment done. Okay. And now we need to prove the opposite containment. Beta contains 0. Okay, so beta contains 0. So start with something that is in 0. Let P to be in 0. Then P is less than 0. Okay, P is less than 0. So I need to show that P is in beta. So to show that P is in beta, we need some minus P, which is positive. Okay, so minus P is positive. Thus, minus P is positive. Minus P is positive, and therefore minus P minus half minus P. Okay, take R to be minus P minus half P. Take R to be minus half P, we have minus P minus R minus P minus R. This is actually I can just take minus R to be minus P. I don't need this half business. Minus P minus R by definition is just minus P plus P, which is 0. Okay, and this is 0, which is not in alpha, because 0 does not contain 0. Right. The cut 0 only contains negative rational, so 0 is not in the cut 0, which is alpha. Right. So R is positive, and we have minus P minus R to be not in alpha, so therefore P is in beta. P is in beta. So P is in beta, it's done. So therefore this proves beta contains 0. Okay, so two sides are verified. So beta is equal to 0 in this case. Case 1 is done. Okay. Case 2. If alpha is positive, you need to show beta is negative. Beta is negative, remember what this means. Or remember what the beta less than 0 means. This is a relationship between, this is an order relationship between cuts. So that means beta is a proper subset of 0. So let P to be in beta. Let P to be in beta, need to show P to be in 0. Okay, so actually, you know what? Let's first say we need to show beta is properly contained in 0. Do you have the proper contained symbol here? Negated relation, this one, yeah. I need to show beta is properly contained in 0. Okay, so first let's show containment. First, let's show containment. This is containment. This is not proper. This is not necessarily proper containment. Let's first show P is in 0. Okay. So let P is in beta, then P is in beta. That means minus P. So we can just say minus P minus R is greater or equal to 0 for some alpha, for some R greater than 0. So that's the that follows from the assumption. Minus P minus R is greater or equal to 0 for some R positive. So what does that mean? Well, so P from here we have p is less than or equal to, thus. Oh, actually this is not a good idea because alpha has changed. I cannot use what's earlier here. Okay, so let me rewrite. Then minus p minus r is not in alpha. Now, is not in alpha for some r positive. Okay. Since alpha is contains 0. Alpha properly contains 0. Since alpha contains 0, 0 the rational number 0 is in alpha. The rational number 0 is in alpha. And here minus p minus r is not in alpha. 0 is in alpha. Thus, minus p minus r must be strictly greater than 0. Okay, where we use the proposition. Going back, proposition 1, I think. Yes, proposition 1. We use this property. Okay. Right here. Here we use proposition 1, i.e. p is less than minus r. P is less than minus r, but minus r is negative. So p is less than 0. So p is less than 0, hence p is in 0. Hence p is in the cut 0. All right. Since p is in the cut 0, all right, that's done. So we have p is in 0. This proves the containment part. It proves that beta is containing 0, but we still need to show that it is not proper containment. It is a proper containment. So we need to find something in 0 that is not in beta. Something in 0 that is not in beta. How do we do that? Okay, alpha strictly contains 0. Alpha strictly contains 0. 0 is in alpha. Since 0 is in alpha, 0 cannot be the greatest element. Okay, so now we then show 0 is not equal to beta. Not equal to beta. So I need to find something that is in 0 but not in beta. Since 0 is in alpha, 0 is in alpha, as we argued earlier, there exists something that is greater than, there exists there exists something that is greater than 0 and is still in alpha. There exists, I already have P, let's write Q. There exists a Q in alpha with Q greater than 0. Okay? With Q greater than 0. So what happens if we P is Q is in 0. I need to show proper containment. Where's my diagram here? So alpha is positive. Alpha is positive. So I need, or I said there's a Q greater than 0 and is in alpha. I want to show that the minus Q is not in beta. Okay, claim minus Q is not in beta. Claim minus Q. Okay, so Q is greater than 0, then immediately we have minus Q is in 0. Minus Q, then minus Q is less than 0, i.e. minus Q is in the set 0, in the cut 0. We claim that minus Q is not in beta. Okay. Okay. For if minus Q is in beta, we try to deduce a contradiction. There would exist R positive such that the negative minus Q, which is just Q, minus R is not in alpha. So what does that mean? Q is in alpha, minus Q is not in alpha, and that's not possible. Contradicting that Q is in alpha. Since Q is in alpha, this is a contradiction. This would be a contradiction. Since Q is in alpha. All right. So therefore we have successfully found an element, aka minus Q, that is in 0 but is not in beta. This proves beta is not equal to 0. Okay? So overall, we have containment and not equal, therefore it's proper containment. This little claim turns out to be more complicated than I thought, huh? My goodness. This is I always knew there is such a thing called Dedekind's cut, and I believe about 10 years ago,
I did something like this, and I spent the whole day of doing nothing but Dedekind's cut, and I proved every single property. Okay, and I have not looked back because it was a miserable experience. Okay, as you can probably see, but yeah, yeah, I think yeah, let's persist. Okay, this is what it takes to be good at math, basically. Okay, um, all right. So beta is less than zero in this case, and that's case two done, right? Let's prove case three. Prove case three. So I need to show. I think this should be easier, no? I think this should be not easier, but similar to case two because it looks quite symmetric. But you never know. You never know these things. Uh, so need to show beta properly contains or the zero is properly contained in beta. Okay. Okay. So that's what we have here. So first, let's prove containment. Okay. Let the thing is, how do I use this condition? Right? How do I use this condition? Because if I have let's say an arbitrary element p is in zero, it is negative, but we don't know its relationship between it and alpha. So already these two proofs are not the same. You can't just say, oh, similarly, when alpha is less than zero, beta is greater than zero. It's not the same. When alpha is less than zero, okay, we need to show that. Can we use contradiction? Let's say, suppose for a contradiction. Because I immediately had an issue because I can't use the condition. If I wanted to show that zero is contained in beta, I let something in zero, but but that thing might not be in alpha, right? Suppose let's say we suppose for the sake suppose for a contradiction that beta is less than or equal to zero. Beta is less than or equal to zero. Okay, i.e. beta is contained in zero. Doesn't have to be properly contained now, right? Um, because beta can equal to zero in this case, or beta is properly contained in zero. So together, you just beta is a subset of zero. Okay, so suppose for contradiction, let's say beta is contained in zero. Let's see what we can get. Okay, so well, um, now I let p, so to say, to be in beta. Then, then on one hand, by definition, and on one hand, by the definition of beta, we have minus p minus r is not in right is not in alpha or some are positive. That's on one hand. And on the other hand, because beta is a subset of 0, beta is a subset of 0, p is less than 0. And on the other hand, p is in 0, and thus p is less than 0. Hopefully we can deduce a contradiction from those two facts. So p is less than 0. P minus alpha is not in, p minus r is not in alpha. So p is less than 0. That means minus p and hence minus p is positive. And minus p is not in alpha either. So minus p is not in alpha. Minus p minus r is not in alpha. How would that be a contradiction? Minus p minus p minus, how would that be a contradiction? This doesn't seem to be working. This doesn't seem to be working. Okay, so let's try something else. Let's try q in alpha. Get q in alpha. So therefore q is negative because alpha is less than 0. Then q is negative. So minus q should be positive. Okay. Minus q should be positive. Minus q should be positive. Therefore, minus q minus half. So minus q should be in beta. And minus q should be in beta. Then minus q, or should we say q is in beta? If something is in beta, I'm getting tired actually. I'm getting slower and slower actually, sorry. If q is greater than 0,
Q is greater than 0, so minus Q, let's do it this way. So half Q is greater than 0. Half Q is greater than 0. This can be understood as minus Q. Is that minus Q? No, not minus, minus. Actually, what I'm trying to say is minus half Q, minus half Q minus half Q is positive. So, and thus minus half Q is in beta. Minus half Q is in beta. Actually, half Q should be in beta. No, half Q should be in beta. Q is half Q should be in beta. I am utterly confused. Okay, so picture. So everything needs to be redone because this is not the order relationship depicted in case 3. Alpha is negative. All right, so this is alpha. I picked an arbitrary element in alpha, calling it Q. So minus Q should be, and by the way, this should be beta, by the way. Beta should be here. This is alpha, this should be beta. So minus Q is up here. Is minus Q should not be in beta. Okay, Q is in alpha. Q is in alpha. Q is less than 0. How do I get a contradiction from that? I suppose that beta is less than or equal to 0. Namely, beta is contained in 0. So to contradict that, I need to find something that is in beta that is strictly positive. I need something here. I need something here. I need to construct something that is strictly positive in beta. How do I do that? Because so far I'm not getting a contradiction. I need something here. Okay, so beta, okay, so alpha is properly contained in 0. There is something in 0, but is not in alpha. Let's start with that. Because if let's say I want from the picture, right? If I want something, please give me a pen. Yeah, thank you. Yeah, if I want something here, I need the opposite to be here, right? So this opposite is in 0 but not in alpha. So that's our breakthrough point.
Okay, so not in alpha. Since alpha is less than 0, since alpha is less than 0, there exists something in 0, but it's not in alpha. That's our hope. There exists some q that is in 0, but not in alpha. I don't know why. Maybe it's because of the OBS, I think. My computer is running a bit slower than usual. I might need a more powerful PC for this. And Q is not in alpha. All right. So Q is not in alpha. So Q is less than 0, and therefore minus Q is positive. I want to claim that minus Q is in beta, which would be a contradiction. Which would be a contradiction. So claim minus Q is in beta. Actually, I can do half minus Q is in beta. No? You know what? Let's just do minus Q in beta. For that, I'm going to I don't know, maybe use a contradiction or what? Q, this is our minus Q, and this is my Q now. To show minus Q is in beta, I need to find something positive such that minus Q, subtract that thing, is still not in alpha. And that's easy, right? That's easy because you can just pick minus half Q. Minus half Q cannot be in alpha. Minus half Q is positive, so it cannot be in alpha. So we're done here. Okay, claim the minus. So we write indeed. No, no, my God. If something is in beta, beta is this set. Beta is this set of elements P such that exist R greater than 0. We have minus P. Minus P minus R is not in alpha. So if I say minus Q is in beta, that means there exists R greater than 0, minus minus Q, which is positive Q, which is not, Q is not positive, but Q, okay, just Q. Q minus R is not in alpha. How on earth do I do that? I know that Q is not in alpha. I know that Q is not in alpha. So based on that, I can write half q minus negative half q is not an alpha. So that will work. So this is, I'm sure, yeah, the initial instinct was right. I need half q. Claim minus half q is in beta. Indeed, the negative of minus half q, let's write that more explicitly, okay? So the negative of half q, subtracting the negative of half q, which is positive, this is exactly q, which is not in alpha. So that's basically done. So the opposite of half q, subtract by a positive real, by a positive rational, is not in alpha. Okay. So let's write, since half q minus half q is, since half minus half q is positive, it is not in zero. I promise, the introduction of complex numbers is infinitely more simple than this. Okay. Yeah, there's a reason that uh, the question about the real numbers, the definition of real numbers, was not solved for over 2,000 years. Okay, so here we have, therefore, this proves this, or is that contradicting? Contradicting beta is contained in zero. Okay, so that's case 3 done. Hence, beta is positive. Okay, so yeah, this proves the claim. This proves the claim. Alpha equals to either you have alpha equals to beta, or you have alpha and beta have the opposite sign. So this is done. Okay. Okay. I'm going to delete this. Okay. So what is this for? What is this for? I wanted to. Did I delete something more than I need? Okay. Yeah, indeed, I'm just starting here. Okay. I need to prove the double containment. That is alpha plus beta is a subset of zero, and alpha plus beta contains zero. Okay. The first containment is easy. The second containment turns out to be very tricky. Okay. So here I can, without loss of generality, assume that so without loss of generality, assume that, you know what, let's do cases. Let's do cases. So that should make things clearer. If alpha is equal to 0, then uh, the opposite containment, how do I, because the main reason we struggled is because we don't know the relative sign of alpha and beta. And now, based on the claim, we we can have cases. So now, in the second part, we consider three cases. Or do we just need consider two cases? Because here alpha and beta are completely symmetric, right? So we consider two cases. Consider two cases. So case one, based on our claim, okay. Um, the first one says, hang on, the first one says when alpha is equal to beta, case one. But if alpha and beta are equal to 0, if one of them is 0, if two of them are both 0, okay, or if they're both 0, then there's nothing to prove based on our previous identity. Something plus 0 is always itself, so there's nothing to prove. Okay, so we can actually put the case before. So it's here. Let's just say to prove alpha plus beta is 0. Suffices to consider the case where alpha and beta are of the opposite signs. From our claim, from our previous claim. So, because if alpha and beta were equal to 0, because that's the only opposite, that's the only remaining situation. If alpha and beta were equal to 0, then what happened? Well, then the identity is trivial. the identity immediately holds based on A4, which we just verified. Okay. I don't know why this is getting so slow. Perhaps it's because the size of the document is getting larger, or it could because of OBS. But either way, next time we will have to start a new node. For if both are 0, then by A4, which we just verified, the identity holds trivially. So, um, so yeah, and without loss of generality, we can just assume alpha is positive and beta is negative. Okay, because um, here, if one of them, if let's say, if alpha is negative and alpha is, and beta is positive, you can just rename the letters. So without loss of generality, assume alpha is positive. Let alpha be positive. So beta is negative. All right. Okay. So that's cool. The first containment needs nothing to be done. Okay. So here, uh, in the second containment, the opposite containment, we're going to continue using what we have here, and we're going to add an extra requirement. So basically, this n here. By the way, let's walk through the opposite inclusion once again. So we want to show that 0 is equal to p plus q for some p in alpha and some q in beta. Okay, so this is what we want. For that, let's take an arbitrary. Okay, we already have an arbitrary r in 0. Okay, so r is negative, and w, which is minus half r, is positive. Okay, so this positive w exists. By the Archimedes property, there exists integer n such that we want n times w to be in alpha. So okay, so so imagine you're walking on the positive axis and taking a step of size w at a time. Because alpha is bounded above, eventually, if you walk enough steps, you will leave alpha. So n to be that very step of the last step where you're still in alpha. So basically, nw is in alpha. This must exist. nw is in alpha, and so that's the critical step. Okay, critical step number. nw is in alpha, and n plus 1w is not in alpha. Okay, so this n must exist. And now we take p equals to minus n plus 2w. So minus p minus w minus p minus w is m plus w, which is not in alpha. Therefore, p is in beta. Okay, p is in beta. So p is in beta. We can write
we have this R. Okay, R is equal to minus 2W. Minus 2W, which is what? Which is P, which is P. P is in beta. I want something in beta. P. And then plus NW. Because P is minus N plus 2W. NW plus P. NW is in alpha. NW is in alpha and P is in beta. So we're done. Okay, finally. Okay, I think we're at the very end of our stream because this proposition is now proven. Okay, so R is in alpha plus beta. R is in alpha plus beta. So yeah. Okay. Therefore, overall, 0 is alpha plus beta is equal to 0. Hence, alpha plus beta is equal to 0. Everything in A5 is verified. And of course, beta is the minus alpha. So this proves the existence of the additive inverse. Okay, so I guess I'll just leave the scratch work here. So, so we're done. Okay, thanks very much for watching. I'm getting very tired, and I apologize for the imperfections along the way. And I think I'll create a GitHub to upload all these notes in case anybody is interested in looking at them after. Okay, and I'll see you next time.